Okay, so we are looking at section 2.3, graphs that enlighten and graphs that deceive. Alright, so the key concept is to introduce other common graphs that foster understanding of data, discuss graphs that are deceptive because they create impressions about data that are misleading or wrong. If you remember from the last class, we discussed misleading graphs, and when we were talking about histograms, we discussed that the bar widths being the same helps prevent any type of misleading impressions. Using technology to generate a variety of graphs. And so we will look more at generating graphs in next class. So we have dot plots, a graph of quantitative data. If you remember, quantitative is numerical. So a graph of numerical data in which each data value is plotted as a point or dot above a horizontal scale of values. Dots representing equal values are stacked. So each value is still represented. So what this right here would mean at the 60, if there's 3 of them, that is 3 60s. That would be 60, 60, 60. Right here, say this is 64, and there's 1, 2, 3, 4. So the frequency would be the frequency for 64 would be 4. And then 70. This would be about 68, and there's 1, 2, 3, 4, 5. So we would write 68 5 times. 1, 2, 3, 4, 5. And so on. So we would have about, this would be about 72. We would write that 1, 2, 3, 4, 5, 6, 7, 8 times. 76, 80, and so on. So if you notice over here, we can see, there's these gaps. And then there's this one over here at like 124. So this is pretty far away from the majority of the data. So this right here is probably an outlier. Okay. Features of a dot plot is displays the shape of the distribution of the data. It's possible to recreate the original list. So that can sometimes be important if we want to actually know all of our data. We can, like we started to do here, we can actually list all of the data. We can have, a 96, a 104, a 124. This would be 88. 1, 2, 1, 2, 3, 4, 5. You would have that 588. So you see we're able to write all of the data pieces. Alright, so then we have stem plots, also known as a stem and leaf plot. It represents quantitative, so again, numerical data by separating each value into 2 parts. The stem is the leftmost digit, and the leaf is the rightmost digit. So similar to the dot plot, we can write out our numbers. It's telling you here, this would be a 60, 60, 60, a 64, 64, 64, 64, 68, 68, 68, 68, 68. This down here would be 124, 104, 96. So this is a stem plot or stem and leaf plot. It shows the shape of the distribution. We can get the original data values, and it is arranged in order. All right, so a time series graph is a graph which are for quantitative data again. And again, quantitative is numerical data that have been collected at different points in time, such as monthly or year. So we see at different points in the year or of years, we collect the data and it is graphed. Some things you can get from this is we can see in what year was the DJIA high, which year was it the highest, and you could see the highest would be here. If I asked you for intervals of decreasing, we could say right here is a decreasing interval, um, another decreasing interval, another one, another one, another one. So we could tell in this time frame right here, we had a pretty, it was continuously decreasing, maybe not at a continuous rate, but it continued to decrease. We can see though that the majority of time, um, the data was increasing. Okay, a time series graph, it reveals information about trends over time. We can look at how things change over time. You could think of maybe like the enrollment at a school, and if they look at that at every year. So, here at Averett, we just had our 165th birthday. So, if we looked at enrollment from year 1 to year 165, we could see some trends. So now a bar graph. So last class we had somebody who said, well, what's the difference between a histogram and a bar graph? So if you remember a histogram, we work with quantitative data, numerical data. Reading the definition here, a bar graph of bars of equal width to show frequencies of both categories of qualitative data. Qualitative, which is your categorical data. The bars may or may not be separated with small gaps. So your bars don't necessarily have to touch in a bar graph. So if you notice here, on the horizontal axis, it's not numerical. These are categorical. We see here favorite sports: golf, tennis, football, rugby, basketball. Also notice there's gaps here, but that doesn't mean there's gaps in data. That's just part of the that's just part of the characteristic of a bar graph. Okay, so features. They show the relative distribution of categorical data so that it's easier to compare different categories. So I do think bar graphs still make it very easy to kind of, look at, okay? I can easily see basketball is the most popular. The least popular, golf, or the least favorite. Notice we could even find like the differences between. We could say how many more people like rugby than people who like golf. So if we said this was about 6, rugby's about 10, that's the difference of 4 times. Each student is 5, so that would be about 20 more students have rugby as a favorite sport. So we can still, analyze these graphs. So here, histogram versus bar graph. We've discussed it, but now you can look at it. So a histogram is for quantitative, numerical. Bar graph is for qualitative, which is categorical. And this was on your last, like 2 quizzes ago. All right, so a Pareto chart is a bar graph for categorical data, so still categorical data, with the added stipulation that the bars are arranged in descending order. So a Pareto chart is basically a special organized bar chart. All right, hold on just a minute so you can look at that. I'll be right back. All right, so Pareto chart is a special organized bar chart. So the bars decrease in height from left to right. Notice it's descending order, which means it goes down. Features, it's a relative distribution of categorical data. You can compare different categories, and it draws attention to important categories. So it brings those most, the higher, like here, the higher percentages, they come first. So you see your networking and newspaper. However, there is a huge variation here. So networking is by far the highest percentage, which it doesn't say what this percentage is like for. I would assume this is for like maybe like how people find out about a business or about a job. Okay, so a pie chart, you probably worked with these some. It's a very common graph that depicts categorical data. So a pie chart is categorical, it's not numerical. And it's broken up into slices of a circle, and where each slice is proportional to the frequency count for that category. Okay, a pie chart shows the distribution of categorical data in a commonly used format. And so you can see here we have, they've taken that Pareto chart that we had and they made it into a pie chart. So each of the slices of the pie chart represent a qualitative, a category. All right, so a frequency polygon is a graph using line segments connected to points located directly above a class midpoint value. It's similar to a histogram, but a frequency polygon uses line segments instead of bars. So if it's a frequency polygon and it's similar to a histogram, is this going to be for qualitative or quantitative data? Yep, quantitative. Okay, so it's a variation of the basic frequency polygon is the relative frequency polygon. So you think about, what did relative frequency mean when we were talking about our frequency distributions and our histograms, and that is the percentages. So relative frequency, we're looking at our percentages. So when we have our vertical axis, relative frequency would have percents going up and down the vertical axis or vertical scale. Here's an example of the frequency polygon. So you see, instead of having, instead of having bars that continuously, go up. We don't have bars. We have lines. So, my bars obviously do not look that great. All right, so relative frequency, you see the difference here instead of having, so over here we had frequency, and over here you would have the relative frequency, so it's percentage. And notice they put two frequency polygons together. And so think for a second about like how that is helpful. So it might be helpful because when we can see them together, it's really easy when you have the two graphs on top of each other like this, or maybe not on top of each other, but graphed together, you can really see the drive-through times and the percents, and you can really compare the McDonald's and Dunkin' Donuts drive-throughs. This might not be two things we would want to compare, but it might be more so. I would think like people would want to compare like Dunkin' Donuts with Starbucks because both kind of coffee and pastry oriented. But you can see that drive-through times are on the bottom, and McDonald's, they had the most, almost half of their drive-through, I guess, experiences would have happened. It would have taken about 150 seconds, so a little less than 2 minutes. Not bad. And so you could even compare though, did Dunkin' Donuts or McDonald's, which had the most, like took the longest, had any of them take the longest time? And so it looks like here that I see that little blue dot, so I'm pretty sure that they both had a 349.5, about 350-second time. It just looks like Dunkin' Donuts after 249. Oh, it's all at zero. So yeah, the 249.5 is where Dunkin' Donuts that was the longest for any of their drive-through times would have been. Because the others here are at zero, and we could say that right here for our dot, because this dot at 349.5 for McDonald's would also be zero. So the 299.5, so approximately 300 seconds. So you can compare. Graphs that deceive. So things you want to avoid when you're creating graphs, but also when you're looking at graphs, like to tell, like, is this, a good graph? Like, is this representing what I want it to in a way that I want it to? So common deceptive graphs involve using a vertical scale that starts at a value greater than 0. So that would exaggerate differences between gaps. So your vertical axis here should start at 0 and go, up at a steady rate so that between each frequency, there's the same difference. Okay, so you can look here. This first graph starts at 10%, not at 0. So it looks like the placebo in this one did like nothing. But it still was on like between 10 and 12%. So the second one is a better representation because it shows both of them starting off at the same point, like at 0%. And you could see the first one, you would say, oh my goodness, OxyContin really, so much more nausea than people who didn't take it, who took the placebo. And while it is true that more people experience nausea when they took the medication than with the placebo, it looks way different when you put it at like an even playing field and start the vertical axis at 0. So, always examine a graph carefully to see whether a vertical axis begins at some point other than 0, so the differences to determine if the differences are exaggerated. All right, so pictographs. Pictographs are drawings of objects that are often misleading. Data that are one-dimensional in nature, such as budgets, are often depicted with two-dimensional objects, such as dollar bills or stacks of coins, homes, barrels, and that's just misleading. A better representation would be the charts that we have talked about prior. So a pictograph, by using pictographs, artists can create false impressions that grossly distort differences by using geometry. When doubling each side of a square, its area doesn't double, it increases by a factor of 4. So that's being multiplied by 4, even though they're trying to just say it doubled. The picture is actually multiplied by 4, so that is very misleading. When doubling each side of a cube, that's actually a multiple of 8. So it just, makes people visually think something that's untrue. You look here, in 1970, 37% of U.S. adults smoked, and in 2013, 18% of U.S. adults smoked. Now, while you can see that obviously the percent decrease. You can see that from the pictures even without the words. But why is this misleading? So it's one thing is like if you look at these pictures, you would think like it went from, you know, everybody smoking to nobody smoking. And while it did decrease, the decrease wasn't even um, a 20% decrease, and um, the size of the smaller cigarette is way less than even half. Like it's more than a 50% smaller picture. So not at all a good representation of the data, but also like you cannot read it. Like you don't, if it didn't have the words with it, like you'd have no idea anything about um, the frequency or the relative frequency or like categorical data um, and the number of people who smoked. You can't tell any of that from this. Okay, so concluding thoughts. In addition to the graphs we have discussed in this section, there are many other useful graphs, some of which have not even been created. The world needs more people who can create original graphs that enlighten us about the nature of data. So there are lots of careers that use statistics. There are lots of times just in your life you might need to analyze something, and knowing these different graphs will help you. It also enlightens you so that you know which kind of graph to use given certain circumstances. Um, so keep all of that in mind. We will next class finish up the chapter 2. So go ahead and finish reading chapter 2. You will have a short quiz, and then we will be gearing up for our test. So I'll be getting some test review. Not every test will we do like a big review, But since there's so much vocabulary, we will do a little bit of review before the test. All right, you guys have a great day.